I'd like to start by thanking the organizers for giving me this opportunity. In this talk, I want to talk about three different problems that might appear very different on the surface, but I would like to convince you by the end that at their core, they all have the same underlying issue, which is how efficiently can we get high frequency sound waves into and out of wavelength scale cavities. So let's begin. The first problem I would like to discuss is the problem of quantum transduction. It's apparent that currently superconducting qubits are the dominant platform for quantum computing. On the other hand, despite the tremendous progress that has been made in these devices, they still have a major challenge, which is illustrated by this marketing image from Google's cryostat. You see this forest of RF cables, and this illustrates the main problem, which is that if you want to send quantum information between two superconducting qubits located in two distant cryostats, there's currently no way to do that. That's because microwave RF cables are very lossy for quantum information. In fact, the only known way in which we can send quantum information over any distance is using optical photons. And that's what a quantum transducer does, is that it takes quantum states in the microwave domain and upconverts them into the optical domain, which allows you to now interconnect two distant qubits. So while this problem is usually faced in the context of superconducting qubits, I just want to remind everyone that no matter what qubit platform you're interested in, they all have interesting transitions in the gigahertz frequency range. And currently, these quantum transducers are also appear on the roadmap of companies like IBM. So before we delve into the details, it's important to understand why is this an interestingly hard problem and what role can acoustics play here. So to understand this, it's easy to understand this. It's good to look at these devices as resonant optical modulators, and then the problem becomes very clear in that you're trying to engineer strong interactions between fields which have very different spatial extents. In particular, microwave fields usually have wavelengths on the order of centimeters, whereas optical fields have wavelengths on the order of microns. So building cavities that can simultaneously confine these fields and engineer strong interactions becomes challenging. And it's also clear from this why acoustics provides a natural solution to this problem, in that instead of engineering a direct interaction with electromagnetic fields, if you take this electromagnetic field and convert it into an acoustic wave, the acoustic wave has a wavelength on the order of microns. And so now you can engineer a much stronger acousto-optic interaction. And that's why acousto-optics has been sort of considered as one of the useful routes to building these quantum transducers. And so this now brings me to the sort of prototype of every sort of piezoelectric quantum transducer that is out there. And so you start with some quantum state, either from a superconducting qubit, or in this case, just a very weak classical signal. You convert it into an acoustic wave, and this acoustic wave is injected into an optomechanical cavity. And the critical parameter here is this phonon injection efficiency. How efficiently can you load these cavities with phonons? Like all nonlinear interactions, you use a strong pump field to parameterize this interaction. And what you're interested in ultimately is this optical sideband photon, which carries all the quantum information that the microwave photon started out with. And now if you look at this, you realize why this is a challenging problem, because it involves a multi-step process. Each of these steps is parameterized by metrics that quantify their efficiency, some of which have to do with the materials, some of which have to do with the device geometry, etc. And the key is to go through this whole loop while maintaining near unity efficiency. A lot of these details are discussed in this review article that we recently wrote, and I refer you to that. But in this instance, we are interested primarily in the issue of transduction efficiency. How can we do this with near unity efficiency? And just to give a flavor for the kinds of problems that are, so just as an aside and for this audience, I'd like to introduce what sort of cavity geometries are used to engineer these kinds of very strong acousto-optic interactions. So one way to think about these devices is to think of them as just simple Fabry-Perot cavities with one of the mirrors mounted on a spring. So as this mirror moves back and forth, it changes the resonance frequency of the cavity. Now, what is important to keep in mind is that there are two different mechanisms that contribute to this change in resonance frequency. One is that the physical length of the cavity changes, which is the so-called moving boundary effect. On the other hand, a much stronger effect, which can be exploited in these devices, is due to the stress optical effect. So as this cavity vibrates back and forth, you generate periodic expansions and contractions, or periodic stresses and strains. And these, due to the stress optical effect, you get a change in refractive index. And in some sense, modern acousto-optics, or this field of cavity optomechanics, relies on finding cavity geometries in which you can confine light and sound deeply at the wavelength scale and engineer very strong acousto-optic interactions. So the prototypical example of these devices are these 1D optomechanical crystals, in which you can confine both light and sound down to the single wavelength scale. And the acousto-optic interaction strength in these devices is many orders of magnitude larger than what you can get in bulk crystals due to this very strong wavelength confinement. On the other hand, this strong wavelength confinement also brings along with it some challenges, which is that it's very hard to excite or load these cavities with phonons from an external transducer. And so this issue of phonon injection efficiency that I discussed at the beginning comes here. And so to see why this is the issue, so one natural way to imagine loading these cavities would be to take a focusing IDT and try and funnel sound into these cavities. But it turns out that these simple tricks or these simple architectures don't really give you high efficiency. And one way to see that is that you get a fundamental mode mismatch here. So the nanobeam breathing modes, which are the ones you're interested in, have a fundamentally shear horizontal profile, whereas standard IDTs in materials like gallium arsenide usually provide sort of Lamb wave-like geometry. So you have this mode orthogonality that you're fighting against. So how do you address this problem? So one way to think about this is that you're asking the transducer to do two different things at once. You're asking it to do both an impedance matching, where you're trying to impedance match to a 50 ohm load, but you're also trying to take the same transducer and sort of doing mode matching at the same time. And these two problems are very difficult to engineer with one transducer. So a few years ago, we proposed an alternative approach as to why not break this problem into two and design a two-cavity geometry, where one of the cavities is a standard RF MEMS resonator, like a contour mode resonator, that does your impedance matching on the front end. And then you have the standard optomechanical crystal geometry that does the acousto-optic interaction. And the trick here is that you design these two cavities, which are very different, to have the same resonant frequency. And so you can engineer a mode hybridization between them. And these mechanical supermodes can be used to increase the transduction efficiency quite significantly. So this effect works very well in theory. So you can see it from the calculations in this paper that the improvement in transduction efficiency is almost orders of magnitude higher, and near unity efficiency can be achieved in this platform. And just for the experts in the audience, this is not really a new idea. So pretty much all resonant gravitational wave detectors use some variation of this parametric transduction readout in their operation. In some sense, we are running this effect backwards here. To build these kinds of devices, it's important to keep in mind that these devices are quite sophisticated. So one of the first things we did at Bristol was to build a photonics platform that was capable of sort of this kind of sophistication. And we choose to work with gallium arsenide for various reasons, but most important of which is that it has very good optical properties and reasonably good mechanical properties that allow you that are suitable for doing these kind of transducers, in addition to possessing a weak piezoelectric coefficient, which, as I'll show, will be the main limitation. So gallium arsenide allows you to basically, so this process, this photonics process basically is derived from a standard silicon photonics process, except that now we will everything suspended. So basically the waveguides are suspended, the grating couplers are suspended. So, and the suspension allows you a natural route towards getting the MEMS inside this process. And so to engineer this kind of mode hybridization, what do we do? So as I said, the ultimate goal is to engineer mode hybridization around these nanobeam-like modes, which have the really strong acousto-optic interactions. But as I said, these are tricky to design around. A slightly simpler problem, and the one that we wanted to study, was that you can, instead of taking the breathing mode of a cavity, you can take the breathing mode of a waveguide and engineer a mode hybridization between the breathing mode of a rib waveguide and a contour mode resonator. So it also has a lot of the same properties, but the problem is much simpler because for reasons that I'm happy to go into in the Q&A. Now, of course, one thing that I did not mention is that this mode hybridization is not without its, so there are trade-offs inherent as in any device design, in the sense that you do get a much higher transduction efficiency, but it's important to keep in mind that the acousto-optic interaction strength does drop off, because now a fraction of the acoustic field starts sitting inside this contour mode resonator away from where the optical field is. So the acousto-optic interaction does drop. On the other hand, what you care about ultimately is the overall transduction efficiency. And on that front, you do get a significant advantage. And so how do these structures look in practice? Well, these are representative images. So you have grating couplers to couple light into these photonic integrated circuits. You have suspended optical micro-ring resonators in which the acousto-optic interaction is being engineered. And the key here is that one arm of this micro-ring resonator is being modulated by this contour mode resonator that's located adjacent to it. And the key here is that we are looking for a mode hybridization between the breathing mode of this RIB waveguide and the resonant mode of this contour mode resonator. And so we achieved that. So currently, because we don't have any tuning knobs, we are currently only able to indirectly infer the presence of this mode hybridization in the super modes. And so one natural question is, how do we do this if you don't have any ways to tune it, given fabrication variation? And in these first experiments, we just made a variety of devices sort of with parameter sweeps and found ones where you get this this crossing between the two resonances. Currently, we're working towards methods to make this more deterministic, and I'm happy to answer this in Q&A. But here's an example of how this looks when it works. So you get this anti-crossing or this mode splitting once you get this mode hybridization. So a characteristic doublet spectrum. But more importantly, you get this very high increase in transduction efficiency. And when you don't get this crossing, when the two modes are not crossing, you only get a single mode response in the RF resonance. Now, I just want to emphasize again that this is, again, an inferred response. So we measure a bunch of devices and we see ones in which you get this doublet splitting. And every time this splitting occurs, you basically get a very strong increase in the transduction efficiency. On the other hand, what you ideally want is some way to directly map out the presence of these hybrid modes. And there are a few ways to do this. One is that you can either measure the thermal noise of these modes, which I'll come to later. But ideally, you want to have some way to either in situ tune one of these modes. So basically, you can either tune the breathing mode or the contour mode across the other resonance. So engineer the anti-crossing in real time, as opposed to just making a bunch of devices and finding ones in which the anti-crossing has occurred. But ultimately, what you want is some way to directly visualize this in situ hybridization. And for that, we are developing some methods to measure these things directly. So a new way because these modes are very tightly confined, traditional microscopy techniques are not able to visualize this kind of mode hybridization. And so because gallium arsenide is a semiconductor, you can use a photocarrier generation as a way to cause local attenuation of the piezoelectric coefficient. And this allows you a way to sort of map the acoustic energy density. In particular, you can start using these kinds of techniques to do mode hybridization. My student Jacob is giving a presentation, so I'll direct you to his talk for further details. So where are we currently with these kinds of ideas in terms of transduction efficiency, and what are some of the key limitations and where? So in the first generation results that we reported in this paper, transduction efficiency is on the order of 10 to the minus 7. So this is photon transduction. So number of microwave photons into number of optical photons out. Now this number might sound quite small, but I just want to point out that this is 10 to the 5 times better than what existed in gallium arsenide before. It's important to also note that in these first generation experiments, the performance was limited mostly by the bare device parameters, and particularly the optical Q and the mechanical Q were not really great. In particular, the mechanical Q was very poor, at the order of only 400, because the contour mode resonator was not suspended well. So you can see that because of the way the waveguides geometries were suspended, we got a lot of leakage. And so now in the next generation devices, now we are much better at. In parallel, we have pushed on all of these fronts, better optical performance, better mechanical performance. And we believe that transduction efficiencies on the order of 1e-3 to 1e-2 are within reach in this platform. And this is something we hope to demonstrate soon. But what ultimately matters for quantum transduction is near unity efficiency. So how do we go that? And there, the piezoelectric coefficient of gallium arsenide ultimately presents a problem. And I believe in the long run, moving towards hybrid platforms like either aluminum nitride with a stronger piezoelectric material like aluminum nitride on gallium arsenide or lithium niobate on gallium arsenide is the way to go to achieve sort of near unity efficiency. So with that, I'd like to switch and talk about a second problem. So in the first set of problems, we are interested in bringing ideas from RF MEMS onto an integrated photonics platform. But you can also take these ideas in reverse and ask, okay, what can integrated photonics teach us about RF MEMS? And so this is an important question to ask, because if you look at all the acoustic wave devices that are currently deployed, RF filters being a very good example, most of the acoustic wave devices that are currently widely used, all of them manipulate quasi-plane waves. So the idea of manipulating acoustic waves with strong geometrical confinement hasn't really had an impact the same way that manipulating light with strong optical confinement has had. And this is basically the simple question that we want to ask is basic. So this is a revolution that has already occurred in integrated photonics, where once you go from optical fibers to silicon photonics and increase the strong geometrical index contrast, you can really shrink the dimensions of the waveguide geometries. And the same question that we want to ask is, suppose you want to monolithically integrate 1 million of these acoustic wave components and figure out a way to do that, then strong geometrical confinement has to play a role. So taking these traditional F-bar like filters, can we sort of do waveguide equivalents of them? And we want to ask basically, how far can these analogies be pushed, and how far can you go along these lines? And so to answer any of these questions, so the idea of guiding sound is in acoustic waveguides is not really new. On the other hand, there have been some very new developments, and the question is, what material platform do you pick, and how do you sort of go about this? So for us, the material platform of choice is mainly gallium nitride on silicon carbide, and there's a few reasons why gallium nitride presents an interesting platform for these kinds of activities. I mean, the natural index contrast or the velocity contrast between the GaN device layer and the silicon carbide substrate makes it very good for wave guiding. As we'll show also, for various unrelated reasons, the epitaxial growth of gallium nitride on silicon carbide has been perfected to the point where the interface defect density has been reduced significantly. And this means that now you can basically have almost lossless waveguiding inside this platform. So, and I'll show some results on where the excess dissipation in these systems can be really, really small. But the main reason for excitement around this and why we believe this is a good platform to study these kinds of devices or these phononic integrated circuits is because gallium nitride has now a foundry infrastructure that one can exploit. But more importantly, because it's a moderately piezoelectric semiconductor, it provides the best platform for doing this kind of active-passive integration. And so while we haven't yet done that, this is the route we are going to take. And so to begin with, we just wanted to show that you can guide sound inside these structures. So you have focusing IDTs that funnel sound into these waveguides, and you can route sound inside sort of wavelength-scale waveguides on these devices. Now, the key point, and this is something that, as I said, I'll keep coming back to again and again, is that while you can do this and you can get very nice proof of principle results, the key issue is insertion loss. So basically, while you can get sound into and out of these devices, the overall transmission coefficient is quite limited. So in our best devices, we are only able to get like minus 20 dB, so only 1/100th of the sound into and out of these structures. And there's a few reasons for doing that, and there's a few reasons why this has happened, and there are many things that we can do to make this better. Some of these ideas are listed here, but insertion loss is the big problem. So while we can get this massive reduction in size inside these devices, there is unless you solve this insertion loss problem, insertion loss is still the main problem that needs to be addressed here. But I also want to point out that you can do more than just sort of reproducing existing devices. So, and there's something sort of qualitatively new that can occur here. And one is that once you can do this, you can also start confining sound using whispering gallery modes. So basically using total internal reflection of sound inside acoustic micro-ring resonators. And why this might be interesting is that once you do that, basically total internal reflection is theoretically lossless. So unlike traditional devices where you're using metallic or hard boundaries to confine sound, here basically you can get much lower loss inside these systems. And so this we can now demonstrate. So we basically have acoustic micro-ring resonators where now the quality factor starts to exceed 10,000 at room temperature. And this is not, I mean, this in a university clean room. So I don't even think we are near the limit. One interesting sort of side note is that actually the Q in these devices is so high that basically it exceeds the fundamental Akiza damping limit of gallium nitride. Why this might happen, I have some theories about it, but this is not something we fully understand yet. But at least one thing that you can take from these results is that the GaN on silicon carbide epitaxy is so good, or the number of threading dislocations at the interface is so little that you don't get any, or at least we are not able to measure any excess dissipation or scattering of sound. Now, this is an idea that's been well known in integrated photonics. That's integrated cavities can get much higher quality factors than just bulk resonators. But I believe this is the first time this has been demonstrated in the acoustic domain. But once you can do that, you can really push this idea further, where now you can start doing things that are sort of qualitatively new, that you could now start building acoustic spiral delay lines where you can start getting massive on-chip delays in footprints that are previously sort of very difficult to achieve in any non-wave-guided geometry. So for instance, we are able to now get microseconds of delay. So I think we have pushed it up to 3 microseconds inside these devices. Loss is still an issue. So we have propagation losses on the order of 3.6 dB per millimeter. But this is something that I believe we can push down further. With the strong geometrical confinement comes waveguide dispersion. But this is something that can be either a boon or a curse depending on how you look at it. So for instance, if you want to do some kind of nonlinear four-wave mixing, you can use the dispersion to engineer phase matching. But again, while right now we can demonstrate all of these interesting things, the theme that I want to keep coming back to is that insertion loss is still a major issue. So you can do all of these new things, but again, the total amount of signal that's getting transmitted from A to B is still quite low. It's on the order of minus 30 dB. And this is a critical problem. So this and needs to be solved if these devices are going to find their sort of use in systems. So with that, I would like to come to the final segment and talk about something completely different. Another application area that might not seem obvious at first, but again, it's limited by the same threshold. And this is the idea of using piezoelectric resonators to do spin detection. And so the key here is, again, it's related to the problem of quantum transduction, is that ultimately, if you look at traditional electron spin resonance systems, they basically have spin sensitivities on the order of 10 to the 12 spins at room temperature. And this is, if you do a back of the envelope calculation, this is many orders of magnitude greater than the fundamental detection limit or the fundamental thermal noise limit. And the main reason, again, is that there is this massive mismatch between the size of your spin system, which is deeply nanoscale, and the centimeter scale wavelength of electromagnetic fields that you're putting on. And so the question becomes, can you use ideas from cavity QED, in particular on strong field enhancement, and see if you can sort of push spin detection towards the thermal noise limit? And this is an idea that's been around for some time. So if you look at the pioneering experiments that were done in the IBM group on using cantilevers to detect single spins, you can see that the spin detection sensitivity ultimately scales with the mode volume. So and so this Q over V is almost like a Purcell effect for spin systems. And related ideas have been shown on the superconducting devices on the superconducting cavity front. But but this requires us to engineer magnetic fields. So and this is the main insight that we had in this work, is that traditionally piezoelectric devices are solved in the so-called quasi-static regime. So basically you assume that you force the magnetic field to be zero. On the other hand, this is not really true, because ultimately you have to solve Maxwell's equations, and this quasi-static approximation is an approximation. So once you go into the gigahertz frequency domain, this is not true. There are two ways to understand why the magnetic field has to exist. Well, piezoelectric devices do radiate, and they radiate weakly, but they do, and the radiation has been measured. More importantly, there is this phenomenon called spin momentum locking. So the evanescent field, electric field on piezoelectric devices, the electric field has to curl, which means that the magnetic field has to exist. And the important thing to ask is basically not that the magnetic field exists, but what is the strength of that field and how does it scale with frequency? And this is where it gets interesting, is that you basically get a very strong scaling with frequency. So basically it scales on the order of f cubed. It scales with the dimensionality. So how strongly you confine the field is how much the local current density scales, and so does the field. I just want to emphasize here that what I'm proposing here is different from, there's been a lot of work on spin detection with surface acoustic waves, but most of those require use of magnetostrictive material. So you're basically using the strain field. We're not talking about the strain field. This is a purely field effect. So there is no contact here. And so how do you verify this? Ultimately, we want to detect spins from single spins or spins of nanoparticles. But in the first generation experiments, just to verify this, we wanted to see if we could do ferromagnetic resonance experiments using surface acoustic wave devices. Why ferromagnetic resonance? Well, because now you can use the collective spin to get you an increase in spin sensitivity. So in particular, you need a sharp feature to be able to observe these things. So what we choose are these magnon modes and EX spheres, and we want to see if you could excite these spin waves in magnons using this. And long story short, we are able to do that. So here's some preliminary results from our measurement. So once you have this magnon mode inside near the focus of this IDT, of this focusing IDT structure, you clearly see a frequency repulsion or an anti-crossing. And but more importantly, you want to eliminate any sources of crosstalk. So you can observe sort of all of these devices radiate very weakly, and so you get a lot of crosstalk effects. But the key thing that we wanted to see is that there is some spatial dependence to this. And this is what the bottom plot shows, is that you basically get a strong absorption signal only near the focus, or there is some spatial dependence, which basically tells us very clearly that this is an acoustic wave effect. With that, I hope I have convinced you that there are very interesting problems that that essentially working with gigahertz sound waves and getting them into and out of wavelength scale cavities is a very interesting problem. And it has applications across a variety of domains, ranging from quantum transducers to RF front ends, all the way to sort of making more efficient spin systems. I just want to emphasize that this is one instance of a more general nanoscale wiring problem. I'm happy to discuss that if needed. With that, I would like to thank all the funding agencies, and most importantly, all the students and postdocs who actually made this work possible. Thank you, and I'm happy to answer any questions.